All right, folks, so let's do a bit more of this beginning assembly stuff. So move is the most common instruction. And by the way, there was a proof recently that move is NP complete. Move is the only command you really need. You can do everything with just move, although that is not normal, and that's what we're not going to do in this course. But the typical move is this way: move source to destination. Now this is called the Intel format with the destination first, where you would subtract 48 from ESP. In the AT&T format, you would flip these arguments, so it's actually more natural, subtract this from that. And that's why when I'm looking at it, and I'm easily confused, I just look for an immediate value here, like 48. And when I see that, that has to be the source, because there is no destination 48. Now there's a bracket 48, which is a memory address 48, and there are things like ESP and EBP, but 48 itself is not a place you can write to, so wherever you see an immediate value, that must be the from address. So anyway, that's the Intel format is the one we're going to use mostly, but there is an AT&T format available too, and I think we'll see it when you're doing Linux assembly here. All right, remember indirect addressing? Brackets around something means you take the value of the thing inside, interpret it as an address, and go there. So here's some examples. Move EAX, EBX. That will take the data stored in the EBX register and copy it into the EAX register. Move 42 into EAX. We'll take the immediate value 42 in hexadecimal and put it in the EAX register. Move EAX bracket this long number. We'll take the memory location at this address, 4037C4, and whatever's in that memory location, it'll put it in EAX. All right, and here's move AX EBX with brackets. That will take the EBX value, look up the memory location at that address, and put whatever's there into EAX. And here's one you'll see a lot. It has a base pointer, EBX, and then the ESI times 4. This is one irritation. The bytes are numbered byte by byte, but in a 32-bit processor, 32 bits of data are moved at a time. So if you do a move operation like this, it moves 32 bits of data. So if you wanted to copy a whole region of memory, hundreds of bytes, you would use a loop like this, where you start here, and then you jump forward 4 at a time. So you increment ESI. So with ESI equals 0, you copy the 32 bits starting at EBX. Then with ESI equal 1, you move over 4 bytes to get to the next 32 bits, and so on. So you'll see this construction quite a bit. An indirect address with a base, and then an index times 4 to make a loop to copy a region of memory. All right, the load effective address is really screwy. It will take EBX plus 8 and put that value in here. Not the memory location put at that value, but the address of that memory location. So it is really kind of a double negative. You use this indirection operator to turn it into a memory address, but then you load the address into there. I don't know why they have this, but it's there. All right. And so here, if you have EAX is 0 and EBX is this number, and then you executed the command move EAX EBX plus 8, it would take the value of EBX, go to that memory location, add 8 to it, and take this value and put it in EAX. So you have all the arithmetic instructions: subtract, add, increment, decrement, multiply, and divide are of course available, so you can do whatever you want. You've got NOP, something we're going to use a lot. The operation that does nothing. If you have a series NOP, 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 each command does nothing. It wastes a cycle of processor time, but the point of this is if you are trying to do a memory corruption exploit, which we're going to do most of the time for the whole semester, you inject code into memory, then you try to run it. And often you're not exactly sure where your code is. So what you do is you have an egg, which is the active ingredient, the code that does something you want. And before that, you put, say, 1,000 NOPs. That's called the NOP sled. And now if you're wrong about where it is, if you get close, you can hit the NOP sled. And if you hit anywhere in those 1,000 NOPs, it will just slide down the sled, NOP, 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 and then run your egg. So a NOP sled is just a convenience used by attackers to make their exploit more reliable, so that it will run even when some of the assumptions you made were wrong and your idea of the address where you're injecting is wrong by some amount. So the stack. This is where you have temporary variables used by a routine and enough information to return from that routine, which is the part we're going to exploit. So every time you call a subroutine, like you're in Microsoft Word and you hit print, so it calls some subroutine to print, it creates a new stack frame. With the ESP is the top of the current stack frame, and the EBP is the bottom of the current stack frame, and in between are the temporary variables stored that are used while you're in the routine. And when you're done, it returns to the calling routine using data that's stored in the stack frame. Push puts data on the stack, making it bigger. Pop takes data off the stack, making the stack smaller. Call enters a subroutine, so that creates a new stack frame, going one more layer deep in the dream within a dream function of your program. Leave returns from a function. Enter is another way to enter a function, and return is another way to come back from a function. So all of these have effects of creating a new stack frame or releasing an old stack frame for reuse. So a small program that does something and returns, like printf, at the start of the function there will be a prologue which creates the stack frame by adjusting the EBP and ESP and reserving enough room for the local variables. And at the end of the function will be an epilogue which restores the stack and the registers to their previous conditions so that when you return to the calling function you can pick up where you left off. So you have a stack frame and another stack frame and caller. So here's the, say, Windows. Here's Microsoft Word. Here's the printf function. Every time you call a function, the stack gets bigger, and you have another stack frame. And when you return from the printf function, you go back to Word, and when you return from Word, you go back to Windows. That's how it works. And inside the stack frame, you'll have variables, and then you'll have the old base pointer, and then you will have the return address. This is what we really care about. The return address is the extended instruction pointer at the point when you called the routine. So you go through your program, and then you call printf. The EIP now points to the next command after called printf. So it stores it here, stores the EBP, and then it does the printf. When it returns, it finds this address, which is where it left off in the calling function. So if we are able to overflow these variables and write a new data on top of this return address, then when it returns, it will return to the wrong place and we gain control of the program. And that's how a buffer overflow works. You find a variable where you can write out of bounds and you change the value of the return address. So it thinks it's finished that function and resuming the function above it, but in fact it is going somewhere else, executing code that you chose. All right, test and compare. We'll compare two values and set the 0 flag if they're equal. You can branch with jump 0 or jumps not 0. Jump will jump if the last operation resulted in 0. Jump not 0 will jump if the last operation did not result in 0. All right, so in C, you start a program at main argc, an array of argv. Argc contains the number of arguments, and argv is a pointer to the names containing these arguments. So if you do copy foo to bar in C, this is a Unix command line command, and it is also a C program, like most Unix commands. And so this has 3 arguments. The first one is CP itself, then foo, and then bar. That's the list of arguments. All right, so if the reason I mentioned C is the simplest language, very closely related to assembly. We'll use a little bit of C programming to understand how assembly works. You don't have to know a lot of C programming. You don't have to know a lot of assembly. We're only doing the simple things here, this class about them. So here, for example, if you were to increment a number, you define an integer variable called number, and then you would number plus plus to add to it. That's what C would be. And when you compile that into assembly, it will look like this. Number, define word, put a 0 in there, and then move number to EAX, increment EAX, and put EAX back in number. Because I guess you don't have the command to increment memory directly. This, by the way, is more common in the reduced instruction set ARM than it is in Intel, that you can't do anything directly in memory. You have to copy it into register, do it in the register, and then put it back in memory. But anyway, as you can see, it takes 4 assembly language commands to do the equivalent of 2 C language commands, and that's why people prefer to write in high-level languages. Here is an if command. You have a number. If number less than 0, do something. So in assembler, you have a number. Then you move it to here. Then you execute an OR command. And the point of an OR command is if these EAX is 0, this will produce 0. If EAX is not 0, the result will not be 0. So now I can use a jump greater than equal. So if it was not 0, go down here. Jump greater than or equal. Okay. If number, I see number less than 0. That's interesting. I'm not sure about this less than 0 part. This may not be perfect. You have to think about some conditions, whether it really gets the less than. But anyway, this is the general idea. This is how you would do an if statement. You would set it up, do some kind of comparison, and then use a conditional jump like this to jump down here. And you'd either do this stuff or you do the stuff down here at label. All right. Here you find an array with 4 variables and then set the second one to 9. So here's how you do that. Array, define word, give it 4 numbers. And then you move 2 into EBX. And then move array, bracket EBX, 9. This will take the value of the array and add 2 to it. Someone says Sam. LDR, STR, or EAX will trigger the signed flag for negative integers. Well, good. I'm glad you know. I did not know that. Good. Thank you. I'd have to go look at the x86 reference manual to get those details. That's the part I'm not sure about, but I'm glad Rainbow Cache had it. All right. And here's a triangle where you take width and height and you make a 5 component array for some reason, and then you just calculate width times height. So the point here is just that you have to take width times height over 2, and here you see it using integer multiplication to do that. And you could try to figure it all out, but I'm not that interested, just to point out it uses the integer multiplication fund. Yeah, that's why JEC worked. Good. Thank you, Rainbow Cache. So this is an example of how you would compare C to assembler. All right. So let's do the last Kahoot, which is here. Trick me into buying something. All right. Looks like maybe we got everybody. All right. So the instructions at the start of a function. All right, that's the prologue. All right, what mnemonic enters a function? Okay, that's call. Okay. All right, what mnemonic will multiply two numbers? That's integer multiplication. There's also floating point multiplication, but I've never used it. All right, what mnemonic will compare two numbers? All right, test will do it. All right. All right, and what mnemonic is especially useful for buffer overflows? NOP for the NOP sled. All right, and what mnemonic shrinks the stack? All right. Pop takes the top value off the stack, making the stack smaller. All right, PJ has won twice. And CCAP wins. And HEMA wins for a second time. Good. All right, I've got my winners. So let me stop this recording.